and also for the last talk of TPMPC, we have an interesting work about concretely efficient secure comparison by Amit, Agarwal, and Stanislav Pecheny, Mariana Raikova, Philip Schoppmann, and Concept. And Amit is going to present this next one to us.
Hi everyone. So today I'll be presenting our work on concretely efficient secure comparison. And as he mentioned, this is joint work with Stan Pecheny, Mariana Raikova, Philip Schoppmann, and Concept. So let's first start with what the secure comparison problem is. So here we have two parties, Alice and Bob, each with private inputs X and Y, and they want to find the result of the comparison X and Y while hiding their private inputs. And the setting that we are considering is two-party setting in the semi-honest adversary model. And also what we are interested in the offline-online model. Here in the offline phase, parties do some random pre-processing. And then in the online phase, when the inputs arrive, they use the pre-processing material to evaluate the function on their inputs. And the focus of our work was concrete online communication efficiency with also practically feasible offline phase. More specifically, we are looking at the following secure comparison functionality. Alice has an input X and Bob has an input Y. They send the inputs to this functionality, which generates a bit B representing the comparison output. And then it secret shares this bit across two parties. So we want the result to be secret shared among the two parties. And why even secure comparison is useful? So first of all, secure comparison is useful in previous sorting protocols. Then it is also useful in machine learning tasks, for example, nearest neighbors, activation functions, splines, sigmoid, and interval containment. And secure comparison also shows up in evaluation of combinatorial problems like max flow and shortest path if you want to do this securely. Why is this problem non-trivial? So first of all, let me emphasize that the question really depends on the way the input is represented. So if the input is actually bit-wise represented, then this is actually simple. But the problem happens when the input is arithmetically shared. And in that setting, when the input is arithmetic shared, the comparison inherently becomes a bit-level operation. And all existing techniques, implicitly or explicitly, have to somehow look at the individual bits to compute the result. For example, using bit decomposition techniques. And this kind of bit probing indeed dominates the concrete communication cost of secure comparison protocols. So let me go over some prior works which try to solve the secure comparison problem. So one of the recent works is based on function secret sharing, as you saw in Lisa's talk. So this is at a high level, a way to secret share a function across multiple parties. So imagine if you have a function f, you can split this function in some way into two pieces, f1 and f2 across Alice and Bob. Now, in the online phase, Alice and Bob can run an eval function on their pieces of the function on an input x to derive outputs y1 and y2, so that y1 and y2 represent a sharing of the actual output y, which is the evaluation of the function on the input x. So now that we have seen this scheme, what kind of functions can we actually secret share efficiently in a concrete sense? So in prior works, it was shown that it is possible to secret share point functions. What are these functions? So these functions have two parameters, alpha and beta. So it takes so the function returns beta whenever the input equals alpha and 0 otherwise. And an FSS scheme for such functions is known in literature as a distributed point function, DPF for short. Also recently, we have schemes for doing FSS for comparison functions. A comparison function has the same parameters, alpha and beta, but it returns beta on all inputs x less than alpha and 0 otherwise. And an FSS scheme for such comparison function is known as distributed comparison function, DCF for short. Recently, we also have incremental point functions, DCF FSS schemes for such incremental point functions, but we'll talk about this later. So this is known in prior works. What are the pros and cons of DPF and DCF? So for now, I want you to focus on these two parts, DPF and DCF. So what are the pros and cons? So the pro is that these constructions are very simple and require only one-way function. And moreover, they enable a concretely optimal two-party equality or comparison protocol. By concretely optimal, I mean in the online phase, parties only interact in one round of communication and exchange a single element with each other. However, the disadvantage of such schemes is that the offline phase is very expensive to be evaluated in 2PC. By offline phase, I mean in this diagram, splitting this function across the two parties within 2PC is very expensive. For example, if you use garbled circuits to do a 2PC evaluation of this red circle region, it will require you to communicate multiple garbled AES circuits across. Another approach which is communication efficient was proposed in prior works, but that requires an exponential amount of local computation per party, where exponential in input length of the function DPF, the FSS function. So it can only be used for small sized inputs, for example, 16 bits. There is another line of works on secure comparison based on non-FSS based techniques. And a common theme across these works is a divide and conquer approach. For example, the theme is the following. So you take your strings that you want to compare and split it into smaller strings, perform comparison on smaller strings, and then somehow combine the results. For example, let's say we want to compare X and Y. We chop it up into halves, X high, X low, high order bits and lower order bits, similarly Y high and Y low. And then we have a nice recurrence relation. So here you see that on the left-hand side of this equation, we are comparing X with Y, and this is nothing. This is equivalent to comparing X high with Y high, XORed with X high equals Y high and X low less than Y low. What this is saying is that X is less than Y when either the higher order bits of X is less than higher order bits of Y, or the higher order bits match and the lower order bit of X is less than lower order bits of Y. So given you have this recurrence relation, there is a nice strategy that you can deploy. So suppose you have your string X and Y that you want to compare and you chop it up into 4 pieces. And then let's say there is some magical way you can compare the smaller strings. So let's say there is some magical way you can compare these small strings X1, Y1, X2, Y2, X3, Y3, and X4, Y4. We'll see how this is done later. And then you can use this recurrence relation to combine the results of comparison on smaller strings to derive the comparison results on larger substrings. In a tree-like fashion, you can combine these results to get the comparison results on your full length strings. Now, how do we do the comparison on smaller strings, right? The magical way that I was referring to. So let's say we have the following parameters. So small l is the size of the original string and small m is the size of the strings after the split. For example, small l can be 64 bits. And if we chop it up into 4 pieces, we get small strings of size 16 bits. Now, a recent protocol proposed by Rathi et al. Called CryptFlow2 uses 1 out of 2 raised to m OT in order to compare these small strings. The problem is that using this 1 out of 2 raised to m OT requires order 2 raised to m online communication. So our approach is the following. We observe that FSS-based techniques provide you optimal online communication and round cost in the online phase, but they have a very inefficient offline phase, except for small inputs. Whereas, on the other hand, non-FSS-based techniques have good offline cost, but suboptimal online phase. So the idea is, what if you use FSS-based techniques as a subroutine inside non-FSS-based techniques to reduce the communication cost? More specifically, we use FSS for comparing small strings and then combine the results using non-FSS-based techniques. The benefit is that this helps you to reduce the online communication of non-FSS-based approach while not adding significant overhead of the FSS-based approaches. Now, let me give you a high-level overview of how the protocol looks like. So in the offline phase, Alice and Bob use a lightweight 2PC to generate FSS keys, specifically keys for DPF and DCF for small input lengths, and prior works can do this efficiently. So in this example, Alice and Bob are generating 4 pairs of DCF keys and 4 pairs of DPF keys. And then using standard techniques of OT and OT extension, they can generate bit beaver triples. We'll see how this pre-processing is used in the next slide. So now that the offline phase is done, we move on to the online phase. So in the online phase, they want to compare X again, string X against Y, and they chop it up into 4 pieces, as I showed earlier. Now recall the divide and conquer strategy that I was mentioning, right? So we will try to compare the small strings with each other. So as a first step, they compare X1 with Y1. These are small strings, remember, and for this, they will use the orange pre-processing FSS material, the DPF and DCF keys, to do this efficiently. Similarly, they will compare X2 with Y2 using the yellow DCF and DPF keys, and so on. So now we have done the smaller string comparisons using FSS very efficiently. And now we'll use the same recurrence relation that I showed you earlier. Note that this recurrence relation has an XOR and an AND gate. XORs are free, whereas for AND you need to do a bit level multiplication. This is where we will use bit beaver triples. And so you can combine them in a tree-like fashion, as I showed you, using bit beaver multiplication to derive the result of comparison on larger substrings, and finally the result of comparison on the full length strings. Okay, so let's do a concrete comparison with prior works. So small l will represent the length of strings that are being compared in bits. So we compare our work with prior work by Rathi et al. Called CryptFlow2, and also a work by Kuto from 2016. So on the column here, you can see the length of the bits. So as you can see, in our online phase, we are 2.3 times better than previous work by Rathi et al. And 3.8 times better than Kuto 16. However, in the offline phase, we are much worse than the previous works. And the main bottleneck here is due to the DPF and DCF keys generation. Although it's still practically feasible, it's more overhead than the previous works. I should mention here that these costs can possibly be reduced in future by developing PCGs for generating DPF and DCF keys. So there is still hope to make this overall efficient. Let me also compare this with pure FSS based approaches. So like if you were to use an FSS for large size inputs, this is how it will look like. So the offline computation cost of FSS blows up. Here you see that FSS requires you to do 2 raised to 64 AES evaluations for inputs of size 64, which is practically infeasible. So the offline cost of pure FSS based approach is infeasible compared to our approach. In terms of communication cost, in the offline phase, we are two times worse than just pure FSS based approach. And in the online communication as well, we are almost 2x worse than the previous, than the pure FSS based approach. So the takeaway here is that combining FSS and secret sharing MPC can lead to good concrete efficiency. And how can we further improve the cost of secure comparison? So one direction is that either to design concretely efficient 2PC offline procedure for generating DPF and DCF keys for large size inputs. If you can do this, then you can directly use pure FSS for doing secure comparison. The other direction is that somehow, as I mentioned earlier, you somehow generate PCGs for generating multiple DPF and DCF keys. If you can do this, then the offline costs of our approach will go down significantly. Okay, so now in the we had some additional contributions while in the project. So we come up with a new DCF construction via black box reduction to iDPF, which I will cover in this talk. We also use this secure comparison protocol to develop concretely efficient sigmoid. And we also propose a new variant of prior Donner-Scheller technique to generate FSS keys for arithmetic shared outputs. So a blueprint of this third point was provided in paper by Boyle et al., but we discovered that there was some underspecification because of which it did not really work. So in the remaining talk, I'll cover this first point. So recall the FSS slide that I showed you earlier. We went over what a point function is, what a comparison function is. Now let me talk about what incremental point function is. So it has parameters alpha and multiple betas. And what it returns beta L if the input X is a L length prefix of the point alpha and 0 otherwise. And an FSS scheme for such incremental point functions is called in literature as incremental distributed point function, iDPF for short. And this was developed in recent work by Bonnet et al. So the intuition of this iDPF construction is as follows. So suppose you have 3 beta values and one and alpha, and let's say alpha is 5, which is 1, 0, 1 in binary. Then the iDPF construction follows a tree-like structure, where the alpha, the blue alpha, indicates the path to the leaf, 5th leaf, and then you have beta values encoded sequentially along this path, and all other nodes have 0 values encoded. The FSS scheme for iDPF allows you to secret share this tree structure across 2 parties using keys K1 and K2, so that when they expand this locally, what they will observe is a secret sharing of the underlying tree structure. The brackets here, square brackets, represent the secret share. DCF, on the other hand, as I mentioned earlier, has this functional property that it outputs beta for all values X less than alpha and 0 otherwise. And let's say alpha is 5, then the DCF tree structure looks as follows. So it has beta values on all leaves until the alpha leaf. For all values greater than equal to alpha, it has 0 values encoded. So the question that we were considering is whether we can construct DCFs from iDPFs. For example, if you have a DCF function f alpha beta, can you construct an equivalent iDPF function with parameters alpha and some beta values? So pictorially, can you change the DCF structure on the left into some kind of iDPF structure on the right? And we show that this indeed can be done. And for simplicity of presentation, we will encode the beta values in the iDPF tree 1 level up. And this follows generically from the existing iDPF construction. So here you can see that the root has a beta value and leaves have no values encoded. So step 1 of the reduction is as follows. First, you find a mapping from the red beta of the DCF to orange beta values of the iDPF. And the mapping is as follows. You look at the ith bit of alpha from left. And if it is 1, you set beta I minus 1 to be the red beta of the DCF and 0 otherwise. For example, if you have the following DCF structure on the left, encoding the orange beta in this fashion will give you the following iDPF tree on the left, right. So alpha here is 1, 0, 1. So you look at the first bit of alpha, it's 1. So you encode beta on the root. The second bit of alpha is 0. So you encode 0 along the second node. And if the third bit of alpha is 1, so again you encode beta. So now you have got this iDPF tree structure on the right. So the second step is now to find a mapping from eval function of a DCF to eval function of iDPF. And here we have the following rule. This rule looks complicated, but let me go slowly through it. And we will explain it in the next, I will explain it in the next slide using an example. So first you do an evaluation of the input X on all I length prefixes. So you compute these green yi values, which are basically length I, the prefix evaluations of X, length I prefix evaluations of X on the iDPF. Then you compute the purple Sj values, which are basically selecting the yj minus 1 values, either selecting or not selecting, depending on whether the jth bit of X is 0 or not. And in the end, you output the sum of all these Sj values. So we have the rule here, and let's see an example. So as we are considering alpha is 5 in our example, and let's say we want to evaluate it at x equals 4. So here I've shown the iDPF tree diagram where the blue line indicates alpha and the yellow highlighted line indicates x, the point where we want to evaluate at. So we go along the yellow highlighted path. So at the root, we see the value is beta. So y0 becomes beta. On the second level, we see the value is 0. So we set y1 equals 0. And on the third level, we see the value is beta. So we set y2 equals beta. Now we compute the purple S values. So S1 becomes either, so the first bit, so the first bit of X here is 1. And by this rule, we get S1 equals 0. S2 equals 0 because Y1 equals 0. And S3 becomes beta because Y2 is beta. And last bit of X is 0. Then we add all these values up and get the output as beta. And this is what you would expect because X is less than alpha. So the output of the DCF indeed matches. We take another example where X is 6, it's greater than alpha. And here you would expect the output of DCF to be 0. So let's see what it is. So again, you go path like node by node along the yellow highlighted path. So you get Y0 equals beta. And on the second node, the value is 0. So you get Y1 equals 0. And on the third node, the value is again 0. So you get Y2 equals 0. Now you compute the S values according to this rule. So the S1 value would be 0 because the first bit of X is 1. So this rule says by this rule, it should be 0. And the second bit of X is 1. So you again get S2 equals 0. And now since Y2 is 0, you get S3 equals 0. And if you add all these up, you get 0 as the output. So the advantage of our DCF to iDPF reduction is that this reduction is completely black box in iDPF. Basically, it makes use of iDPF interfaces in a black box way to get the required DCF functionality. And this means that in practice, you can implement your iDPF and iDPF and reuse the same implementation to get a DCF functionality. And we also see this as a simpler construction compared to the DCF construction in previous paper by Boyle et al. And also the concrete efficiency parameters like key size, running time of gen and eval matches the efficient construction in prior work by Boyle et al. Thanks.
Thanks for talking. Are there questions? Yes.
Yeah. Thanks for nice presentation. I have one question. What is the round complexity for comparison?
Round complexity is a log of the length of the string divided by the number of pieces that is split up. So it's actually log of number of pieces that you split into. So if let's say your string is 64-bit length and you chop it up into 4 pieces. So the round complexity will be log of 4. It depends on the number of splits that you're doing. So note that if you do lower number of splits, right, then you will have to use an FSS gate for large size inputs. So basically, if you make the splits each size of the piece smaller, then it increases the round cost. But it also lets you use FSS for small size inputs. But if you make the pieces larger, you reduce the round cost. But now you have to use an FSS for large size inputs. So it can be seen as a tunable parameter, like depending on how much offline computation cost you can bear, you can tune the parameter to get a trade-off between offline computation cost versus online rounds.
But then you have an imbalance in the information you send per round, right? Because now you have a lot of small FSS instances. So you,
Mhm.
okay. Are there more questions? One more, okay. Why not?
So why the comparison was restricted only to those works, and like, there are a couple of other works which focuses on comparison, protocols called data comparison, like Rabbit and why? Like, how is your protocol compared to those works?
Yeah, I'm not aware of this book. I mean, did you see any, like, yeah, I saw at a couple of works. So the works that I looked at actually claim to be better than prior works, this Rathi et al. And Kuto et al. So those seem to be the state of the art, these works, in terms of online communication costs.
For example, there's on paper 80/2. They have comparison like 100 bits in online.
100 bits.
300.
I think they have a kappa parameter, right? Okay. Okay, sure.